Hey everyone! In this video, I'll be showing you some tools and techniques for recovering private keys or for getting started with legacy type wallets, pay to public key hash, and their keys in hexadecimal format. In a second video, we'll be able to demonstrate using keys in the WIF format. However, we'll do this in separate videos because that way we can utilize specific tools, thereby achieving greater speed and significantly increasing the chances of recovery. As I've mentioned, I will begin with keys that are in hexadecimal format. These are 64 hexadecimal characters, which, as you might expect, will generate a legacy type wallet. It is characterized by starting with 1. On this website, we have a brief summary about puzzle wallets. We also have a few download links available, like Key Hunt and BitCrack. In our examples, we will be primarily utilizing BitCrack first. It's important to note that puzzle wallets also begin with the number 1. The first example is where the missing or corrupted characters are grouped together at the end of the key. Let's start by copying the key that we suspect is corrupted. Then we'll open BitCrack . The second parameter we need to consider is the key space, which is what we'll be referring to as the key space. It's structured as the initial range, followed by a colon, and then the final range. So what you're going to do is take the key that has all of those missing characters, and you'll substitute the initial range with a 0 and the final range with an F. Let's go. Key found.
For my 1660, it has a speed of 166 million keys per second. It took 9 seconds.
We only have 8 characters missing in our current example. If there were 9 characters missing, it would take something like 5 or even 10 minutes. As the number of missing characters continues to increase, the required time will also grow exponentially. It's obvious that the specific hardware being used will greatly influence this search time. It's quite interesting that with this particular type of key, you can effectively divide the range and then execute the search across several different computers. Let's move on to our second case, which is when the corrupted characters are found in the middle of the key. When I say in the middle of the key, it could be in any position, whether at the very beginning or at any other point, as long as these characters are grouped together. So the initial parameters remain exactly the same. BitCrack followed by 2 hyphens, then key space, and finally the initial range. Colon, final range. Within the final range, we are going to replace all corrupted characters with the letter F. Now, dak, daktoms. Well, now, different from our first example, we have the stride parameter. To calculate the stride value, you'll need to count the number of characters that appear after the very last corrupted character. In our specific example here, we have exactly 11 characters, so the stride will be 0x1 followed by 11 zeros. And then, finally, we will add our address. Alright, the key's been found. It took a bit longer because this example had 9 characters instead of 8. It took 4 minutes for 9 characters. I believe it's quite worthwhile to talk a little about BSGS, as it's an algorithm where we achieve incredible speed, but we do need to have the wallet's public key. The wallet's public key is exposed whenever there's an outgoing transaction, as is the case with the wallet used in our examples. This is the website that holds the wallet we're using in our examples. I'll be demonstrating how to obtain that public key. Alright then, let's take an outgoing transaction. Here, we have the public key exposed. Besides the exposed public key, you need your corrupted characters to be at the end of the key. Here, I used Key Hunt in BSGX mode. 17 characters were found in 41 minutes. You will need to adjust the -k parameter according to your RAM memory. Here, we have the file containing the public key. The -t parameter would represent the number of threads, and the range follows the same format as the other examples. So, if you had the public key for wallet 71, you would be able to utilize BSGS and retrieve your bitcoins with great ease. In 2019, some wallets had their public key exposed. That's the reason they've been resolved. The last one was 130, which was even resolved using the kangaroo algorithm, which is another algorithm that also uses the public key. It was solved by Retired Coder. There are about 30 characters. Fortunately, Retired Coder shared his code in one of his posts on the Bitcoin Talk forum, and he commented that he had used approximately 20 RTX 4090 graphics cards. Finally, let's move on to the last situation, which is when the private key has its characters corrupted and scattered throughout the key itself. For this specific problem, I developed the Kamuka X tool. It was developed from a fork of CUDA Brain. CUDA Brain is a tool designed for brain wallet resolution. After cloning the repository, you'll need to configure the generation for your graphics card. In our case, it's 75. You need to configure it in the makefile. It's also important to configure the number of blocks and the number of threads, but this will vary greatly depending on your graphics card's capacity. You will need to generate the hash 160 file for your address. To do this, you paste your address into the addressing.txt file and then execute the Python script. Take the generated hash file, paste it into the hash folder. Don't worry, if you don't know your address, I'll show another solution that generates the hash file from several possible wallets. So, we're going to go ahead and compile Kamuka now. I'll first run the X mode, which is designed to substitute any missing or corrupted characters with the letter X. Because I haven't explicitly set the -k parameter, the system will automatically retrieve the necessary key from the key.txt file. Here we have our private key. I'm going to show you that now, using the -k parameter. For some reason, it failed to recognize the X character within the PDF. The code has now been corrected. I had forgotten to verify for an uppercase X. In this example, it will take a little longer because there are 8 positions. The first example was 7 positions. Let's wait for it to finish. He found the key. He still continues searching even after he has found the key. Maybe one day I will correct this. This was our X mode. We also have the combinate mode, where you can repair a private key without knowing the exact position of the corrupted characters. The -p parameter represents the maximum number of corrupted characters to be searched for. For a demonstration, I took our known private key, altered 3 of its characters, thus simulating a private key with 3 corrupted characters. We're going to execute this in combinate mode. The -k parameter is for specifying the partial key, which in this case is the corrupted key, -p, and it will then search for up to 3 positions. A small bug where the key was found across multiple threads. The linear mode is merely a concept, because since it searches for ungrouped characters, it would be much faster to use a tool that employs point addition. As I mentioned previously, I'm going to simulate a scenario where I don't know the address that's generated from the private key. For this purpose, I extracted every single address that had its first transaction in the first half of 2015. I took into account all wallets, even those that currently show a 0 balance. Of course, for a real case, you can filter only wallets with a balance. I used the first half of 2015, as that's when the Puzzle Wallets transaction took place. Once that was done, it generated a CSV file. I took that CSV file and converted it into a TXT. After that, I executed the Python script, which then generated the hash file. I also needed to make some adjustments to the hash count parameter. It takes a little more time to start up, but it's already finding the puzzle wallets. The private keys are also saved in the keyfound.txt file. I will pick one of the keys that were found and check which wallet it belonged to. So, this was the private key for wallet 25. This was just an example for wallets where you don't know the address. I ran some tests now with an RTX 3070. We can see that the speed doubled. I had to use a slightly lower power limit as the card was repaired. I don't trust the quality of my soldering or the dubious components. Our project is an amateur one, so there may be errors, just as this video may also contain errors. For a real search, always run offline. Even after inserting a partial key, never reconnect your computer to the internet. Just because a project is open doesn't mean it's safe. Always monitor your graphics card temperature, use a quality power supply, and that's it folks. If you have any questions, leave a comment.